This video focuses on Charles' law and Gay-Lussac law, which discuss the proportional relationship with gas parameters. Charles' law, you have a proportional relationship between a gas's volume and temperature. So what that means is they either both increase together or they both decrease together. If you had a graph to represent volume and temperature data, as the temperature increases along the x-axis, the volume, represented along the y-axis, increases accordingly. If you look at this and you say, let's say the temperatures decrease, okay, going along that way on the x-axis, what happens to the function on the y-axis? It decreases accordingly as well. So the parameters either both increase or both decrease. Okay, the equation here represents that relationship. Your initial conditions, your final conditions. Okay, so the initial volume over the initial temperature is equal to the final volume over the final temperature. An example that you can think of, okay? Think of a balloon. The balloons appear inflated, higher volume, in warmer temperatures, and they appear deflated with the lower volume in cooler temperatures. So increased volume with increased temperature and decreased volume with decreased temperature. Okay, so let's say that you go and you buy a balloon for a birthday party. Let's say it's a hot July summer, and you go to the store, Party City, dollar store, wherever, and you buy helium balloons, and inside the store it's air conditioned and it's cool, and they fill your balloons up and they look real, nice and inflated, okay? And then you go outside and it's really hot outside, and maybe one of your balloons burst, which can happen because the temperature increased, so the volume increases. Likewise, let's say that you buy a balloon for a birthday party, and let's say it's cold December, and you go into the store and it's nice and warm, and they fill your balloon up, it looks really nice, and then you go outside into the parking lot and all of a sudden it looks like your balloon has shrunk. You're ready to go in and say, hey, you didn't fill this up with enough helium. No. The volume decreased because the temperature decreased. Okay, and you can, if you have any balloons in your house, you can, try this in your house with your freezer. Blow up a small balloon, okay, and then put it in the freezer for about 10 minutes or so, and you'll see that it shrinks, okay? Not drastically, but you'll see that it shrinks, okay? So we have this formula that we're going to do some sample problems with now, okay? Now, when we did Boyle's law, we looked at pressure and we looked at volume parameters, and the units were the same for pressure and for volume within that problem. Now we have temperature. When we do gas laws that involve temperature, temperature units must be in Kelvin because the gas laws were derived from the absolute temperature scale of Kelvin. So we want to make sure any gas law that has a temperature in it, we need to have that temperature in Kelvin. So we're going to see that Charles' law, okay, will have the temperature in it, and the one that we do after it. Charles' law is named after Jacques de Charlet. I know I'm mispronouncing it. I know you students that speak French, you're probably chuckling right now that I'm saying it wrong, and I apologize. But it was named after that scientist who did the experimentation with gases. Okay, so temperatures must be in Kelvin for all gas law problems. Okay. So let's do a problem. Let's say we have 3 liters of oxygen gas. stored at a low temperature, are stored at negative 20 degrees Celsius, okay? But they warm, the 3 liters warms up to 27 degrees Celsius. So 3 liters of oxygen gas are stored at negative 20 degrees Celsius, but when warmed up to 27 degrees Celsius, the volume changes. What is the volume of the warm oxygen? Okay. So we have 3 liters of oxygen gas stored at negative 20 degrees Celsius, but warmed up to 27 degrees Celsius. Okay, and the volume changes. What is the volume of the warm oxygen? Now, we do have negative temperatures a lot in science, okay? So I don't want you to always think that we have always positive numbers. Okay, we do not. We have temperatures below 0, okay? And, you know, the gas laws have a lot of applications in a variety of fields, in science, in engineering, in healthcare applications, okay? We have so many applications where gases are applied. We need air to breathe. Air contains oxygen. You don't have the oxygen in the air, then you're not going to last very long. You have a lot of engineering applications which use pneumatic powered equipment. Pneumatic meaning powered by gas. Usually it's by air because that's the most abundant. Okay, so you know, the gas laws have a lot of applications in a variety of areas. All right, but let's get to solving this problem here. And again, we have word problems. All right, look at the units that go with the numbers. We have liters for volume. We have Celsius for temperature. But we need to convert these Celsius temperatures to Kelvin. Before we start plugging anything into formulas, convert the Celsius to Kelvin. Okay, I think it was back in chapter 3 where we learned to convert temperatures. So let's convert our temperatures. So we have 2 temperatures here. We have negative 20 degrees Celsius and we have positive 27 degrees Celsius. So we add 273 to convert from Celsius to Kelvin. So we have 253 Kelvin for the negative 20 Celsius, and we have 300 for the 27 degrees Celsius, okay? So these are the temperatures that we're going to use in the formula, okay? So that's our first step. Now our second step is to plug in what we have into the gas law. Second, we want to set up the equation. V1 over T1 equals V2 over T2. Now, like I did with the Boyle's law examples, and like I'm going to show with all the gas law problems that I do in these videos, I'm not going to rearrange this equation right now. If you like to do algebra that way, and you know right away what variable out of all these you need to solve for, and you want to rearrange that equation, you could do that, okay? But I'm going to pretend that you don't know how to do that, okay? And you look at the numbers that you have to plug in. Now we have the initial volume. The initial volume was 3 liters. And the initial temperature is the 253 Kelvin. The final volume we don't have. That's our V2. That's our unknown, okay? And our final temperature that we have is 300 Kelvin. Okay, now we want to solve for V2. Okay, now I'm old and I like to do cross multiply, and I know that some people are not taught it that way anymore, but if you weren't taught it this way, I'm going to teach you this way. You may like it better. Okay, you can use reciprocals. Math is math, and you'll get the same answer whether you do cross multiply or do reciprocals. But cross multiply makes things really simple. You take one numerator and multiply it by the other denominator. That's one side of your equation. So 3 liters times 300 Kelvin. That's one side of your equation. Equals the product of the other denominator times the other numerator. 253 Kelvin times V2. All right, we get rid of this whole fraction setup when we use cross multiplication. Okay, now we have it looks like a Boyle's law problem, okay? So we clearly see we need to find V2. So we divide both sides of the equation by 253 Kelvin. Okay, so cross out like terms. On the left-hand side, Kelvin is the same, okay? So now we have 3 liters times 300 divided by 253. Okay. Let me just make sure to keep that 3 sig figs, 3 sig figs. Okay. So our final answer would come out to be 3.573. Okay, this non-terminating decimal. All right, but we will put it with 3 significant figures because all of our measurements had 3 significant figures, including our initial temperatures, which were in Celsius. So we keep our final answer with 3 significant figures. It would be 3.56 liters. Okay, would be the volume. All right, does it make sense? Well, what happened to the temperature? The temperature started at negative 20 Celsius and went up to 27. All right, or we could say went from 253 Kelvin to 300 Kelvin. You had an increase in temperature. So the volume should increase in proportion to that. So we had an initial volume of 3 and we had a final volume of 3.56. Okay, so they both increased. All right. Let's do another example with Charles' law. Okay. Let's say that an application that you're doing in the lab requires use of a glove box, and a glove box will keep all of the air out. It'll keep out all the oxygen in the air, all the water vapor in the air, and in that glove box you're going to have argon gas, okay? So let's say that 22 liters of argon gas. Remember, argon is a noble gas. It doesn't react with anything, column 8A of the periodic table. 22 liters of argon gas. Okay, let's say that it's in use for some application, but let's say that the argon gas, 22 liters of argon gas are compressed to 14.6 liters, okay, after cooling from 100 degrees Celsius. What is the temperature after the gas cools? Okay. Now, when you see in the textbook problems, all right, you're going to see problems worded a little bit differently, but the math is the same. Always look at what parameters you're given in the problem. You're given numbers with units. The units are your friend, okay? Let you know information that you have. You have a volume, 22 liters of argon gas. You have another volume, 14.6. The volume went down, okay? You have 22 liters and it's going down to 14.6. After it cooled from 100 degrees. So we had it 100 degrees Celsius, okay, pretty hot, and the volume went down. As a result, the temperature we should see go down. All right, so we want to find the temperature. Okay? So first we need to convert any temperature that's in Celsius to Kelvin. Okay? So T1, 100 degrees Celsius, we want to convert into Kelvin, 373 Kelvin. Okay? So now we want to set up V1 over T1 equals V2 over T2. The initial volume that we start off with is 22 liters. And the initial temperature, it's at 100 degrees Celsius. Its Kelvin equivalent is 373 Kelvin. Okay, we need to have the Kelvin temperature. If you accidentally put in the Celsius temperature, you're going to get the wrong answer. Okay, and it won't just cancel out, because if you think, how do you go from Celsius to Kelvin? You're adding 273. It's not like you're dividing or multiplying by some factor. No, you're adding 273. All right, let's look at our problem. Do we have V2? Yes, we have it, 14.6 liters. Do we have the final temperature? No. That's our unknown. That's what we want to find. Okay, let's use cross multiply. Cross multiply. One numerator times the other denominator. Numerator's on top, denominator's on the bottom. Denominator D, it's down on the bottom, DD. Okay, so 22 liters times T2 equals the product of the other numerator times the other denominator. 14.6 liters times 373 Kelvin. Okay. Now we need to divide both sides of the equation by 22 liters. Okay, so this cancels out, liters cancel out, and now we have T2 that we can solve for. So 14.6 times 373 divided by 22 will give us 248, if we round to 3 significant figures, Kelvin. Okay, now the question did not specify for the temperature to be in Kelvin or Celsius. It just said what is the temperature after the gas cools. So if we're not asked to have it in a specific unit, okay, 248 Kelvin. But if you were asked to put it into Celsius, then you would subtract 273. It would be equal to negative 25 Celsius. So it would be 248 Kelvin or negative 25 degrees Celsius. If you were asked to put it into, convert it back into Celsius, okay? But you were not. But if you were, that's how you would do that, okay? Because remember, to go from Celsius to Kelvin, you add 273, but to go from Kelvin back to Celsius, you subtract 273. Okay. The next gas law that we're going to do is called Gay-Lussac, the Gay-Lussac gas law. And that's another simple gas law, and it's very similar to Charles' law. The only difference now is that instead of volume, we're going to have pressure. So let's do an example of the Gay-Lussac law. The math is just the same as it is for Charles' law, except instead of volume conditions, we're going to have pressure conditions. Okay. Remember, when you're taking notes, as if you were in class, you can always pause the video on the screen, okay, and copy stuff down, okay? I only have one little board here. It's not like I have all the boards that I'm used to, but you have the capability of doing pause and writing it down and going back and making notes of any questions you have that you can email me later, okay? Okay, the next gas law that's still categorized as a simple gas law is the Gay-Lussac law. Okay, again, this is named after a French scientist who did work with this. With the Gay-Lussac law, you have a proportional relationship between a gas's pressure and temperature. So they both increase together or they both decrease together. And again, if we had to graph data that's related to this, all right, we would have the temperature on the x-axis and the pressure on the y-axis, and we would see an increasing function here, okay, because they're proportional. P1 over T1 is P2 over T2, initial conditions, final conditions. This gas law involves temperature, so temperatures must be in Kelvin, just as we had to put them into Kelvin for Charles' law. So temps must be in Kelvin. Okay. So you see, as the temperature increases, the pressure increases as well. If the temperature were to decrease, okay, decrease along the x-axis, you would see that the y-axis values representing pressure would decrease as well. Some applications of the Gay-Lussac law, when you talk about weather and you hear that there are low pressure areas in the forecast. Low pressure areas correspond to lower temperatures or a cold front. If you hear that there are high pressure areas, that's referring to warmer temperatures coming in or a warm front. This gas law has an application with pressure cookers. Pressure cookers, they cook the food faster because they increase the pressure inside that container and it increases the temperature faster. So increase the pressure, increase the temperature, the food cooks faster. Okay, it doesn't work the same way as a microwave. A microwave works by having the water molecules in the food move around. So they cook differently. They work differently. Also, an autoclave, which is used to sterilize medical equipment, has high temperatures with high pressure in order to kill the germs at the high temperatures. Okay. Another application of this law here, cars are now equipped with tire pressure sensors. Now, back in the day, they didn't used to have this. So within maybe the past 15 years or so, okay, give or take, you have these tire pressure sensors that are in automobiles. So when the tire pressure drops, the sensor goes on. What happens with these sensors sometimes is when it gets really cold, you could have, let's say, one day where it's not so cold, and then overnight the temperature drops drastically. And then you go into your car and you see that the tire pressure sensor is on, telling you that you have low tire pressure. And you think, oh, there's something wrong with the tire. Well, those sensors are very sensitive. Sometimes only a difference of 2 psi will make that sensor go off. What's happened is that because the temperature has dropped so drastically, you've had a decrease in temperature and the air inside your tires has decreased as a result of that, alerting your sensor in your car to go on. So that's something that is a result of this gas law here. Before you used to have these tire pressure sensors, you're always told to check your tire pressures when after the vehicle was at rest. So because after you ride around in a vehicle, the tire pressures will read higher because the temperature is higher from driving. So therefore you would get a reading that would be higher. So all different applications with this. So let's see. Relates to tire pressure sensors, low temps, lower pressure readings, pressure cookers, autoclaves, meteorology terms. Warm, cold fronts. Okay, these all relate to this gas law. Okay, since the math is very similar to Charles' law math, we'll do an example with this gas law. Okay. So I was talking a lot about tire pressures. Let's do a problem that has tire pressure readings in it. Okay. Air pressure in a tire had a reading of 28 pounds per square inch, okay, PSI. At a rest temperature of 27 degrees Celsius, okay? After driving, the air inside the tires increased to 65 degrees Celsius. Okay. What is the tire pressure reading at the warmer temperature? Okay. So again, more word problems. The gas laws. We have a lot of word problems here. Okay. So what we need to do, we have to convert the Celsius temperatures into Kelvin. Okay. Before we do anything with any formula, we need to have the Celsius temperatures in Kelvin. So first, convert Celsius to Kelvin. Okay, so we have 27 degrees Celsius and we have 65 degrees Celsius. Okay, and we need to add 273 to those numbers. Okay, and we have 300 Kelvin for one, and the other one we have 338 Kelvin. Okay, so we're trying to keep everything with three significant figures. All right, so now we have everything in the correct units that we need it for. Okay, so now we can set up our equation. Set up P1 over T1 equals P2 over T2. Okay. Okay. So the initial pressure is 28 psi. Okay. So those tires have a reading of 28 pounds per square inch. Okay, you see? No, wait a minute, what am I doing? Okay, right there. All right, pretend that was the reading, okay? Temperature, 27 degrees Celsius, but we need the Kelvin temperature, 300 Kelvin. The new pressure we don't know, but the temperature we know went up, so we should see that that resultant pressure should go up as well. And the new temperature, it went up to 65 degrees Celsius, okay, driving around for quite a while possibly, or it's just really hot outside. You went from a cold environment to a warm environment, but that's what the new temperature is. Let's do cross multiply. One numerator times one denominator equals the product of the other numerator times the other denominator. Okay, so we have 28 psi times 338 Kelvin equals 300 Kelvin times P2. All right. So now we want to solve for P2. So we want to divide both sides of the equation by 300 Kelvin. All right. So I'm going to just erase the word problem here so I can show the rest of the math up here. Okay, so we want to find P2. Okay. So we have 28 psi times 338 over 300 equals the new pressure. Okay, I just took this part here in the corner and I just wrote it up there. I just so it's a little bit larger. Okay, keep those 3 sig figs. All right, so the final pressure is 31.5 psi. Okay. You say that's not that much. It went up from 28 to 31.5. But you know what? That may be enough for a sensor to go off if it went the other way, if it was a decrease, okay? So if the temperature were 65 and went down to 27, that may be enough of a temperature difference for that sensor on the vehicle to show low pressure, even though it may not really be that low, okay? It's still a good idea to check it, to make sure that that's all it is and not something more serious, okay? All right, so we have Charles' law and Gay-Lussac law, both proportional relationships. Charles' law focuses on volume and temperature, and Gay-Lussac focuses on pressure and temperature. And anytime you have a gas law that involves temperature, you need to have that temperature in Kelvin. Okay, the next video we'll talk about the combined gas law and the ideal gas law. Okay.